Welcome to the computer graphics practice video, and the task is Bezier Spline C++ video. Now in this task we'll be creating Bezier splines with C1 and C2 smoothness. In the task or in the materials you can see this Bezier curve example. You can have multiple segments here, and those are C0 because the splines are connected in one point, so one control point is shared between them, but the derivative at this point isn't continuous because there's this sharp edge or corner here, and yeah. So in this task we'll create those smooth C1 smooth splines and also C2 smooth splines. Now, first thing we want to do is draw something like this. Now, if you open the base code, you should see something like this. I also added this Bezier CPP. This basically is a port from 3GS that creates those Bezier curves with 4 control points. But you don't need to worry too much about this. But what we do have here are a couple of functions. So first, generate random curve points and generate test curve points. So there are two kind of sets of control points. One is this set of test control points, which are fixed coordinates, and you can use those to check is your result correct or not. And the other is just randomly generated control points here. Okay, next we have create spline. So this creates a spline, smooth 1 and smooth C1 and smooth C2. Take the existing control points and modify them in the way that the resulting curve from those will be either C1 or C2 smooth. Then there's also a scale spline function. So in the end of this task there is this thing that you should scale the control points in either X or Y and see if the curve behaves as expected. And there's also sample spline, so this samples the spline points and also the updates spline. We have 2 vertex array objects and 2 vertex buffer objects. So why 2? Because if you think about, you can also see it in the picture here. So if you think about this, then we have at one side we have the control points. So this is some set of control points somewhere, and lines between the control points. And then we have the actual curve, which I don't know how it here goes, something like this. Which also has some set of points on it, and we just take many of those points on the curve and put small lines between them, and this will give us this curve. So this is why we have two vertex both array objects and buffer objects. So they were named spline and spline points. I think this is spline. And points is the spline points and they both have a vertex buffer object in them for their positions. Okay. So what else? Yeah, test points, random points, current smoothness. The random distribution generator. So if you in the soft vertical chopper task, if you used C++11 random distribution, then this is probably something that you did. You can specify like integer values from this distribution, it's a uniform distribution, and so on, and then you can roll the dice anytime you want. Okay, this generates those random points, this generates those test set points. And this creates you the splines, so the spline vertex array objects, also the spline points position, vertex buffer object, and spline position vertex buffer object. Okay, in the update spline we should update those buffer objects. This will smooth the control points depending on your smoothness function, or if there's no smoothing, then we just pass the points along. This samples the spline, so basically if you have the control points, this will give you a set of points that are on the curved spline from the control points. It creates those Bezier curves and gets a number of points on the curves. Then of course draw spline, we draw them with uniform colors. C1 smoothness, this is where you should implement the modification of control points for C1 curve, and this is where you should implement it for C2 curves or splines. Scaling, you implement scaling here in the end, and that's pretty much it. Yeah, so down here, this is just what happens with the spline. You have some set of points, you smooth them, you scale them, and you update the spline by sampling new spline points, and then you draw the spline. Now, if you run this code, then you should see something like this. You have some set of points, lines between them, also curves are visible, and if I press up, then it should say random. If I press down, it takes the test set. If I press right, it's C1 smooth, C2 smooth, and if I press left, it's C1 and C0. So this is how it currently should work, but as you can see, nothing actually happens. And nothing happens because in this update spline method, we haven't implemented the update yet. So when we have changed the points, what we want to do, we can see this update spline is the last function that's called, so we already have the correct points here. What we want to do here is we need to update the vertex buffer objects. So we first need to take the vertex array object, so bind vertex array. We take the spline points, let's update those first. So we bind the current vertex array object. Now we need to bind the correct vertex buffer object. So for this we can see how that is done, for example, in this shader util. So we have this bind buffer, and there's also the bind buffer data. So maybe something like those are what we need here. We bind a buffer, we want the vertex buffer object that corresponds to the spline points. That was the spline points position vertex buffer object, and now we're going to send new points to that. And those new points are those all points. Now, how do we send them? See, it's done here as well. Basically, this is a standard library vector of GLM vector trees. So what we need to do is we need to take the reference to the first object in the standard library vector and the first coordinate of that object. So this is the first float pointer, basically, or the reference to the very first float in this structure. And it's going to read GL floats. Now we need to take this size, so how many vec3s are there, and we multiply it by 3 because they're vec3s. This is how much data we read from this array of floats. Okay, so this is the points, and now I guess we can probably even check, is there going to be some change in the result? So yeah, now if I press up, so up generates me new random values, I can see that the lines and the points change. If I press down, I get the test set, so those red points now correspond to the test set. Okay, but the curves aren't updating. So this is the second part here. We basically do exactly the same thing, but now what we want to bind is not the points vertex array object, but we had spline vertex array object, and this has the spline position vertex buffer object handle that corresponds to the correct buffer. Now the data we send there are those sample points. So sample spline, as you remember, takes the control points, creates Bezier curves for like every 4 of them, and samples around 20 points for each of the curves. So this sample points is the array we want to read the data from for the entire, like for the curve part of the spline. Now let's see if this happens correctly now. And yeah, so when I press the keyboard, then this image appears. Now this is exactly what we had in the task description as the first image. So yep, you can compare it visually, it's the same. So we have done everything correctly so far. Okay, cool. Next thing we want to do here is create these smoothness functions. So currently just the points are passed along and here as well, but we need to be able to modify those points so that the resulting curve is C1 or C2 smooth. You can read from here what does this actually mean. So the derivative in one end of one of the curves is 3 times the vector of the last segment. And in the beginning it's 3 times the vector of the first segment. You can go to this link as well, it should explain you where those derivatives actually come from, but this is what we have. Now we want to make the derivative in the last end point of the first curve and in the first point, like first starting area of the second curve to be equal. So we set those things to be equal, and what we get that not point or the middle, like the shared point, needs to be exactly between those two, so that these lengths are equal. This means that those values will be equal, this means that the derivatives will be equal in the joint point. Now, intuitively you can also see it, so if you move along this line with some speed, you continue moving on the same line with the same speed. So the first derivative is intuitively equal here as well if you have this geometrical construction. And yeah, so we can try to do this. And how do we do it then? So we need some kind of a loop, because there's plenty of different curves in this spline. So we need a loop, let's say, and where should we start with this loop? So let's see what points exactly do we need to modify. And for this, let's draw some points. So I don't know, we have some number of points, so P0, P1, P2, maybe P3. Now this P3 is the same as Q0, so Q1, because we're dealing with cubic curves, right? 1, 2, Q3, which is the same as some R0, and so on. And those are all the points that we have in the loop. So let's see, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, maybe 9. So if we have R0, so R1, R2, and R3 should be the last point, right? And the shared point, so the ones we need to modify are this one, so this is shared, then this one is shared, and that's all that's correctly shared. So we can see that its first point is the point with index 3, and the second one is with index 6. So this gives us kind of a step of 3, but the first and the last points shouldn't be taken into account. Like the goal is to move this point now to be in the middle of the previous and next point, and this one as well. We move it so that it's in the middle of those neighboring points. Okay, so our loop should start from 3, as we So it should, how much should the loop go? So it's something like, what do we have? We have the points or smooth points, the vector is copied, basically smooth points size, but because we don't want the last point, so it's something like -1 or maybe -3 would also be there. And we loop 3 at a time, so the step is also 3. And then we have those smooth points. We take the ith point, and what we want to do is we want to assign a value to it. And if we look at like change its value, and if we look what should be its value here, so it's the same point, this b3, then this is half of the previous and next points. So basically it's 0.5 times the previous point. What is the previous point? It is just I minus 1 plus the next point. What is the next point? It's I plus 1. Okay, and maybe this is it. So let's see, there is an error. Yeah, so float. Yeah, and now we are back here, and if we create a test set and go to C1 smoothness, so this is C0 and C1, then we can see that these points here have moved to be in the middle of the neighboring points. So that one goes here, this one goes here, and that one here goes here. And we get this curve. And if we look at the example here in the task description, and this is exactly that curve. So this is the correct result. You can see the curve is quite smooth compared to this, where there are sharp corners. And this is C1 smoothness. The next thing you would want to do is implement C2 smoothness. So for this, this will be a little bit more trickier. If you look here, and this is not intuitive as well, so what is the second derivative at the shared point here? So it's like impossible to tell via just the geometry. But in the link above, it's calculated that it's 6 times the last point minus 12 times the point before plus 6 times the point before that. And in the first starting point of the curve, it's 6 times the current point minus 12 the next point plus 6 the next point. Now those equations, we can say they need to be equal again, and we get this. So we can divide them by 6 and we get this result. Now we can rearrange the terms. So here is P3 minus P2. Let's pull this out as one term. Then we have P1 minus P2 left in the second term, and with Q as well. What this gives us, it gives us some vectors on the plot. So a vector from Q1 to Q2, from Q1 to Q0, and so on. Now, what's going to happen next here is that we need to somehow kind of simplify it a bit, or make it so that we can create a geometrical structure. So we have P3 minus P2 plus P1 minus P2. So that's on one side, and on the other side we have Q2 minus Q1 plus Q0 minus Q1. So this is the formula we have. Now, one thing we know is that P2 minus P3 is equal to Q1 minus Q0. This is the condition we had for C1 smoothness. So for C1, this needs to hold. If we want to talk about C2 smoothness, then there needs to be C1 smoothness. So we can assume that this needs to hold. So using this, we can kind of rearrange the terms here. And I made a small mistake here. So actually, this should be 3 minus 2. And now if we assume this, we can kind of substitute some values here. For example, if we take this Q0 minus Q1, so this is the negative of that. So that is minus P3 minus P2. We can take this term, put it on the other side of the equation, and we get 2 times P3 minus P2. And this one we can also put to the other side, is equal to Q2 minus Q1, and let's make it a plus, P2 minus P1. So this is one equation we get from this. We can also do the same thing, not to substitute the P1, the Q values here with P's, but the P values with Q's. And it gives us the same result, just that now it is also equal to 2 times, and this term is Q1 minus Q0. Q1 minus Q0. So those three things need to be equal. And what do those three things tell us geometrically? So you can look at this drawing. So basically, we probably should draw it here as well. Let's keep this last formula. So this is the condition that needs to hold for the C2 smoothness, in addition to the C1 smoothness condition. So let's have P0, P1, maybe somewhere there is P2, P3. This probably is in the middle of Q0, Q1, and maybe somewhere, I just put it down here, Q2 and Q3. So those are the control points. So basically we have a blue vector, and that is P2 minus P1. So that is this vector here, and we can see this vector here. So this is the blue vector. Next we have red vector, so that is from Q1 to Q2. So this is this one, and that is that one. Now the sum of those needs to equal 2 times P3 minus P2. Which needs to be the same as 2 times Q1 minus Q0. So what are those Q1s and like those two vectors? These are basically these vectors here. And if you take them 2 times, well, this is the entire length of this. Okay? And you can see P3 minus P2, this is from P2 to P3. From Q1, from Q0 to Q1, this is from Q0, this point, to Q1. 2 times of this needs to be equal to the sum of those vectors. We know that this is like this point is exactly in the middle of this goals of the C1 smoothness. What does this sum tell us is that if we add those two together, like the blue and red vectors, we need to get the green vector. One way we can geometrically do this is, let's try to extend this to some point, and let's try to extend red backwards as well, by the same amount, some point. So, and we can see that they don't like meet at a single point. But in order for the sum to work, they need to. So basically, there needs to be a point up here where the blue vector and here meets with the red vector, which is also here. Now, one way we can kind of try to fix this drawing correctly is to make this blue vector a bit bigger. So maybe P1 is like somewhere here. So, and also there is this P0 somewhere. So the blue vector would be a bit longer, bit longer, so maybe somewhere there is where it ends. And the same thing with this red. So the Q2 is perhaps here. So this means that this red vector is also longer, and it meets up with the blue one at a very specific point up here. And in the task, this point is called a tip, and this is basically the only point you need. So in order to define this C2 smooth Bezier spline, well, you do need like the first two P0 and P1, and the last two Q2 and Q3, but for each joining curve in the middle, like you only need this tip, because given this point and P1, you can find where P2 should be. It should be exactly in the middle of this distance from P1 to the tip. And also this Q1, this needs to be in the middle of the distance from the tip to Q2. So you can find out grammatically the coordinates of P2 and Q1, calculate them based on the value of the tip. And of course the last value here you can take as in the middle of those calculated P2 and Q1. Okay, so this is how this C2 smoothness works. Now, geometrically, this is what's depicted on this drawing. You can see that the addition of this blue and red should give you this purple line. You can also try to derive it from like below, so geometrically, if you add them together, add those together, then like, if you add them together here, then this should equal to that, and so on. Now, the problem you might run into, or you will like most definitely run into, is that what if you have more segments than like 2? You see that for each those segments, like for example the red segment here, Q, the curve Q, this length and this length need to be equal. Okay, so this is what we derived. But for the next segment, so this is this green R curve here. We also know that this part of the curve of this vector needs to be equal to this length. So we get kind of those three vectors here, or three distances that need to be equal, because two of them need to be equal and two others need to be equal, so they all need to be equal. And this tells us that to find the points between the different segments from the tip values, we need to divide this length from one tip to another by 3. So 1/3 along is this point Q1, 2/3 is this point Q2, which is also R1. This is something you also need to consider here. And yeah, so this is the drawing without like that many vectors drawn into it. So at the first in the first part, like those segments need to be equal. In the middle, those 3 need to be equal, and like in each middle part, there's again 3, 3, 3, until the last part where again 2 of those need to equal, and those points are in the middle of those calculated points. So this is just like we did in the C1 part. And all the data you need for defining a new segment in between is just this tip value. And in the end you will get like the line, basically something like this, like a black line here. And it should look like this with the test set, and like this with the random set. And then it's pretty much done. Just implement this function here, following a similar logic that's here, but a bit more complicated, because now you need to have those trees here. For the tip value, you can just take the whatever value like this point had before and use this as the tip value. And yeah, that's pretty much the whole idea here. Also scale the spline, and then you're done. I hope you find this task interesting. So it's about like following this mathematical construction, this stacks construction. You can also look at this PDF. So it talks more about this, how to build it and so on. It has like it tells you how you should define the different control points so that the curve is smooth. Pretty much the same thing I just did here, except that the notation is a bit different. So if you implement the algorithm directly from this article, then be sure to see like what points this notation corresponds to. And yeah, so I hope it's cool, and this geometrical way of like trying to think and like prove and see like what points you actually have and how do the curve control points need to be in order for this to be C2 smooth. I hope it's something cool for you. And good luck and have fun.